Assalamu alaikum, dear students. Moving on to the next lecture. Today we will discuss with a problem of the series solution, in particular with the series solution of the Bessel's differential equation. So if you remember, we discussed the Frobenius series solution for the Bessel's differential equation, and here is the page of my notes before you. Now what is this problem? You must keep in mind that this is the recurrence relation. Aj plus 2 is equal to minus Aj 1 over j plus 2 into 2n plus j plus 2. Okay, so you know that n is positive for the first root of the indicial equation, which we took k is equal to plus n, and the other root of the indicial equation is that k is equal to minus n. So as long as k is equal to plus n, there is no problem. We get all the coefficients from the recurrence relation as we did here, and we reach to the first solution, this one, which we call the Bessel's function of first kind. So that solution was corresponded to k is equal to plus n. Now, to get the second solution, we need to replace k is equal to minus n. So if we put n equal to minus n, then this term becomes minus 2n. And you know that j is an integer which varies from 0 to infinity. Supposing this n is equal to 3, so that this becomes minus 6. This term becomes minus 6, and when we are putting the various values of j from 0, so this is minus 6 then, and when j is equal to 4, this becomes plus 6, and we get this term equal to 0. So if n is a negative integer, then somewhere we will have this term equal to 0. So what happens when this term is 0? Obviously, this is an indeterminate coefficient, so it becomes infinity. It means that the coefficient blows up, and therefore we will not be able to get the second solution corresponding to k is equal to minus n. The first solution was obtained, but the second solution will not be possible provided we use k is equal to minus n. So that is the problem with the second solution of the Bessel's differential equation. We won't be able to get the second solution. Right. So what should we do? We require the second solution. Now here are two important concepts. The first concept is how to get the second solution, and these two solutions must be linearly independent. They should not be linearly dependent. Now, what do we mean by linear dependent solutions and linearly independent solutions? Supposing y1 is the solution of the differential equation, and the second solution is y2. Now if you put y2 is equal to some constant multiplied with y1, that is a constant multiplier of y1, the first solution, so that will also serve as the solution of the differential equation because this differential equation is homogeneous, and therefore but this solution, which is a constant multiplier of the first solution, in fact is linearly dependent on the first solution and is not acceptable. So we would require the second solution in the form of certain polynomial multiplied by the first solution. That will be the second solution. Okay, so let me see if I have mentioned somewhere here, or maybe in the book you can see this. Let me see. Page 450. Let's go to the page 450 first. And see if I have discussed two linearly independent solutions, and then we will move on further. Okay, so this is the topic, linear dependence. So in fact, to get the linearly independent solutions, say y1 and y2 are linearly independent, and if this is the first solution, as you know, this is the first solution of harmonic oscillator and this is the second solution of harmonic oscillator. So this is y1 and this is y2, and this is the derivative of y1 dash and this is the derivative of y2 dash, and the determinant of y1, y1 dash and y2 dash is being calculated here. And if this determinant becomes 0, okay, so listen carefully, if this determinant is equal to 0, it means these two solutions y1 and y2 will be linearly dependent and we do not need this y2. So we need a y2 so that this determinant is not equal to 0, as is the case here. So if this determinant is not equal to 0, then that solutions will be acceptable. Okay, this determinant is known as the Wronskian. We will refer to this later on. So this is the word Wronskian, and Wronskian is equal to the determinant of y1, y2, derivative of y1, derivative of y2. That is called the Wronskian, written as capital W. So this is the first point I wanted to discuss, and the second point is over here. You can see these concepts from my notes as well, but let me come to this theorem, Fujis Theorem. As I told you that sometimes we are not able to get both solutions, and sometimes we are able to get one solution and the second solution is not possible, and sometimes we get both these solutions. So how do we know by looking at the given differential equation that whether the series method will give us both solutions or it will give us just one solution, or it may not give us any solution? That is very rare that we are unable to get at least one solution from the series method. Most of the cases we get at least one solution. But we had to know before we apply the series method, that whether this method will be successful fully or will be successful partially. So this theorem gives us the criteria, and this theorem states the main thing of this, the main paragraph of this theorem is written over here, but let me read. When we are not able to get both solutions, and when we are able to get partials one solution, and when we are able to get the both solutions. Okay, for this we have to go back to what we discussed earlier, the types of the points of expansion. So you must remember that we discussed three types of points of expansion. One was the regular point, in which both polynomials px and qx are not equal to 0, and the second type of singularity, the point was the regular singular point, in which px and qx may be 0, but when you multiplied px with x minus x naught and qx with x minus x naught square, then they become finite. So in that case we say that our singular point is a regular singular point or non-essential singularity. But if still these two terms, that is x minus x naught into px and x minus x naught square into qx are both infinites, they remain infinite, in that case we call the point of expansion to be an irregular singular point or essential singularity. So now what is Fujis theorem? Fujis theorem states that if the point of expansion is a regular point, then you will get both solutions from the series method. That is the first step. The second step is that if the okay, here is the statement. If we are expanding about an ordinary point or at worst about a regular singularity, the series substitution approach will yield at least one solution. So that is Fujis theorem. It means that if the point of expansion is an irregular singular point or essential singularity, then you may not get both solutions from the series method, but this is very rare. The other criteria is written in these three steps, that is also the part of the Fujis theorem. Okay, so let me now go back to the concept how to get the second solution. This is the page of my notes which describes the linear dependence and the Wronskian. Okay, now let's go to how can we get the second solution if it is not available from the series method. So this is the technique by which we can get the second linearly independent solution. Okay, first of all we will calculate y1, which is y1, y2, y1 dash, y2 dash determinant, and this is equal to y1, y2 dash minus y2 into y1 dash, equation 5.1. And this is the equation we want to solve to get the second solution, provided the first solution is given. Okay, so we will take the derivative of Wronskian, w dash will be the derivative of this, and this derivative will contain 4 terms, and this is, when we simplify this we will get this equal to y1 by y2 double dash minus y1 double dash into y2. Okay, so from here we write this is y1 and this is y2 dash, because this is the solution of this differential equation. So if you put y is equal to y2, you will get y2 double dash equal to minus px into y2 dash plus qx into y2. So this is what is written here for y2 dash. Similarly, in the second term, y1 double dash is written as minus px y1 dash minus qx into y into y2. So this is the derivative of Wronskian, and when you expand this, this becomes equal to minus px into y1 y2 dash minus y1 dash into y2. And you know that this is Wronskian, so we have the expression 5.13, that is the derivative of Wronskian is equal to minus px into w. Okay, so we move on further, and well, one page is missing here, which I have not included, but you can find that page from my notes, and from that page you will see that the expression for the second solution is given by this one. Let me see if I can find this from the book. No, it is not from this book. Okay, this is the second solution. This is written here. Okay. So you must consult page 470 and 471 for the complete derivation of the formula for the second solution, provided the first solution is given. And this is the formula which you must note, that the second solution is given by this expression: y2x is equal to y1x into WA, which is the Wronskian at x is equal to a. Now the integral from a to x, exponential of minus integral px1 dx1 divided by y1 x2 whole square. So don't worry about the derivation. You can find the derivation from my notes and from this book as well. So this is the formula in case, and here we will, to simplify this, we will take WA is equal to 1 and we will take the lower limits, contribution from the lower limits equal to 0, to reduce, to simplify this formula as the equation 8.83, that y2x is equal to y1x integral up to x exponential of this and this. So this is the simplified form of the expression for the second solution, and we call this the Wronskian double integral formula. So what is the name of this formula? Wronskian double integral formula, because it contains double integration over here. And px1 dx1 is the polynomial px at x is equal to 1, and so on. So this is how you get the second solution. And applying this onto the as an example, let us apply this formula to the case of harmonic oscillator as we did here. Let me go back to the book. here is the application of the second solution. Suppose we did not know the second solution of the harmonic oscillator and we only knew the first solution, y1 is equal to sine x. Then applying this formula, we get y2x is equal to sine x integral up to x dx2 over sine square x2, because px, this px for this harmonic oscillator, you know that there is no term with y dash, so it means px is 0. So we have taken px is equal to 0, and then we have integrated this and we got the second solution. So sine x, the first solution is used in Wronskian integral formula, and we are successful to get the second solution. So this is how this formula is established, and it gives us the second solution. Okay, so this is how we will get the second solution if it is not available from the series method. And we have now applied this formula to get the second solution of the Bessel's differential equation, as we notice that sometimes the Bessel's differential equation does not furnish the first solution. So here is the differential equation, and supposing the first solution is known as j naught x with n is equal to 0, and the second solution is not available, so we get the second solution by substituting the first solution in the Wronskian double integral formula, and this is what we have done here. And in the denominator we had y1 x2 whole square, and this is the j naught x2. So this is the series. I have written the series instead of j naught x2, and then you can follow these steps over here, which you may not find from the book. So follow these steps and you will get the second solution of the Bessel's differential equation. Right, so this is how we are now able to get both solutions of the homogeneous differential equation, and we have the second solution, both solutions. Okay, now this page, this portion of the page represents that if your differential equation is with constant coefficients, okay, if px and qx are constants, then you do not need to go through the series method. You can write both solutions by this simple technique that you you can follow these steps to see how to get the series, how to get solutions for differential equations with constant coefficients. So in that case you don't need to go for the series method. So go through this. So okay, let me now stop here. We have fully discussed the differential equations, the homogeneous differential equation, and the solutions of the homogeneous differential equation. Now in the next lecture we will learn how to solve non-homogeneous equation, that is when the right hand side of the differential equation is not 0, then how to solve this. Okay, so follow my notes and the pages of the book as I have shown here to completely understand this lecture, and then I will assign you certain exercises next time, and you will be able to, you must solve these exercises. Okay, thank you very much.